Hi everyone, this is Jose Roca and I will present flow of a suspended microcapsule through a constricted channel. This work was made possible by the LMMP lab, PUC-Rio, with the support of Professor Marcio Carvalho and Professor Ivan Meneses. Flow of suspended capsules can be found in different applications, from red blood cells to suspension of capsules in porous media. Red blood cells in biological systems have received a lot of attention over the years. We can find different numerical and experimental analyses on finding what parameters affect the flow. For instance, some diseases can modify the stiffness of the cell membrane, affecting blood circulation. In porous media applications, by using suspension of microcapsules, we are able to reduce water mobility and enhance oil recovery. We block preferential water flow path and divert water to pores with oil. In these pictures, we can see how the capsule gets deformed in order to flow through a constriction. Experimental results show that there is an extra increase of the pressure at the inlet, related to the presence of the constriction. In general, suspended capsule flow is a challenging problem because we need to take into account the complex interaction between fluid and solid phases. This problem depends on different parameters, including the surface capillary number, defined as a ratio of viscous to elastic forces.
In order to understand the dynamics at the microscale level, a constricted channel, the one on the right side, can be used as a model of a pore throat connecting two adjacent pore bodies. This problem is defined by the interaction between fluid and solid phases. For the fluid phase, momentum and mass conservation equations for incompressible Newtonian fluid need to be solved. For the solid phase, on the other hand, membrane dynamics is governed by equilibrium tensions on the membrane. Thus, two domains are needed, for the fluid domain, which is fixed, and for the solid domain, the blue one, which moves and deforms as time evolves. In order to solve the interaction between the capsule and the fluid, we utilize the Merz boundary method, IBM. Both domains are coupled by the FB term, where FB represents the force that the membrane exerts on the fluid, modeled as a volume integral along the solid volume omega s.
This is a 2D planar flow. On the right side, we draw a free body diagram of a membrane segment. We have included forces along the S1 direction and the fluid force acting on the solid. After balancing forces along the S1 direction, neglecting second-order terms, and considering a massless membrane, we obtain this expression. After that, we can divide by the volume of the membrane segment in order to obtain the force per unit volume of the solid acting on the fluid.
We consider that the membrane material follows Hooke's law, with E as a constant of elasticity of the material and Nu as the Poisson ratio, where while epsilon 1 is a strain which depends on the arc length of a given membrane segment at any time t, and the arc length of the membrane segment at an stress condition. Therefore, T1 is expressed as follows, with T0 defining a pre-stress condition which depends on pre-inflation parameter alpha. Thus, alpha 0 means that the capsule is completely relaxed at the initial time. Alpha greater than 0 means that the capsule is pre-stressed before flowing. The membrane position x is updated by the integral of the velocity times the delta function along the whole fluid domain omega f.
Regarding boundary and initial conditions, on the left side at the inlet we impose a parabolic velocity profile. On the upper side at the wall, no slip, no penetration. On the right side at the outlet, develop flow and zero output pressure. On the bottom side at the symmetry plane, no vertical flow, zero tangential stress, and a geometrical condition for the membrane. At T0, zero velocity and pressure fields are defined. The capsule position and the pre-stress condition are also known. We use finite element method. Then we required that the weighted residual equations for momentum and mass. Fluid domain was divided into quadrilateral elements velocity and pressure were approximated with a linear combination of a finite number basis and basis coefficients. Natural boundary conditions are applied by computing boundary integrals. Essential boundary conditions are imposed by replacing the corresponding residual with a desired velocity value. Detailing the formulation of the residual of the FV term. Recall that FV represents the force that the membrane exerts on the fluid, modeled as a volume integral along the solid volume omega s. After using a property of the delta function, we obtain this equation, which tells us that by evaluating the weighting function W at the x member position, we can compute the interaction between both domains. For the 2D channel flow, we have this equation. At the symmetry plane, the contribution of the first term is trivial, because the momentum conservation in the y direction is substituted by the essential boundary condition V equals 0. We finally obtain this expression that can be implemented as. Notice that we have two different grids. Grid of quadrilateral elements for the fluid and a 1D linear segments for the membrane.
The nonlinear problem is addressed by Newton's method. The transient problem uses a predictor-corrector algorithm. Predictor step is forward Euler method, and the corrector step is the first-order implicit Euler method. In order to update the membrane position, these equations need to be integrated, which requires to interpolate U at x. Thus, an inverse mapping scheme was implemented. This scheme allows us to obtain the local coordinate for a given global coordinate.
Regarding the time stepping scheme, first we solve velocity and pressure fields at time k plus 1 by keeping xk and the membrane stress fixed. The nonlinear system R is solved using the MATLAB direct solver. Second, we interpolate U at time k plus 1 using the inverse mapping to evaluate velocity at x. Then we update the membrane position, and finally we repeat. Now we present some results. The constricted channel flow is governed by 5 parameters: capsule radius, the constricted ratio, the pre-inflation parameter alpha, Reynolds number, and the surface capillary number.
As we can see, the capsule moves through the constriction and gets deformed in the process. Notice that at the rear region of the membrane, there is a concave shape at this surface capillary number. At the bottom side, we have 3 plots. The first plot on the left side is the velocity and the inlet. Initially, we impose a 0 flow rate until we reach the steady state. The second plot is the pressure difference between inlet and outlet. Notice how pressure behaves in time. Pressure increases until it reaches its maximum when the capsule is close to the constriction. The pressure peak is of paramount importance to our study. The third plot is the area of the region contained by the membrane. We look at it because for some cases with lower surface capillary number, there is a slight variation of A. Here, there is another configuration for a lower surface capillary number. Observe that the capsule is stiffer and gets less deformed after the constriction. In fact, unlike the previous case, at the rear region, the membrane is convex shaped. These pictures help us in the visualization of how the stress is distributed along the membrane at different times. At the initial time, a uniform membrane stress is observed. As capsule moves, the front end of the membrane is under higher stress than the rear end. This time corresponds to the maximum membrane stress. After the constriction, the capsule relaxes and the stress falls. We also observe the minimum fill thickness between the capsule and the channel wall for different surface capillary number. We can see that for a given radius and pre-inflation parameter, we can fit a power law equation. We can run different simulations for different surface capillary number. The lower the surface capillary number, the stiffer the capsule, the higher the pressure peak. We can also test other parameters such as capsule radius and pre-stress conditions and find different curves. The intensity of the blocking mechanism F is defined as a ratio of pressure difference of the single-phase flow to the maximum pressure difference of the capsule flow at the same conditions. F is only effective, i.e. lower, if the local surface capillary number is low enough. Finally, we study the flow of a suspended elastic capsule modeled as a 1D membrane through a 2D planar constricted channel, a pore throat model, to evaluate potential pore blocking. The set of equations was solved using finite element method with immersed boundary method. Results show the influence of the pre-inflation parameter alpha, the surface capillary number, and the dimensional radius on capsule dynamics and blocking factor F for a given Reynolds. Thank you for your attention, and I would like to thank these institutions.